Much, and thank you everyone for joining us for this session. I am very much looking forward to spending an hour with you talking about big data and analytics, and we've got quite a bit to cover, so let's get straight into it. The first thing I wanted to cover was, what is big data? Now obviously this term is being used a lot in the industry and hyped a lot as well, but I wanted to really talk about it in terms of the tools and techniques that make up this space. And so if you look at this type of graph that a lot of you are very familiar with, that we see all the time about the amount of data that we're generating, that's kind of a given now. We all know that. But I think the interesting thing is the second line on this graph that talks about the data that's actually available for analysis. And so you can see a massive gap there between the amount of data that we're generating and the actual data that's available for analysis. And this, for me, is where big data really plays. So big data, as I see it, is the tools and techniques that we use to basically address that gap. Now, the reason that there is such a discrepancy between the data that we're generating and what we're able to analyze is because our traditional tools are simply not geared for the volume and the types of data that we're now generating. And now I'm talking specifically about databases that we've used for 30, 40 years to collect data tend to work with very structured data sets in a very batch-oriented way. And what we're seeing now is we're seeing a lot of unstructured data and we're seeing a lot of streaming data. And this is why we need these new big data tools to basically help us address that. So if you look on this slide here, we often talk about the data that we have along two vectors. One is the size of the data sets from small to large, and then also how structured is it. And so if you look at some of the technologies, you'll see that the traditional database that we're all used to sits in that bottom left-hand corner there. So fantastic for small data sets and very highly structured data sets. But as you start to branch out, as the volumes grow and structure becomes less, you start to need different tools. And so one of the tool sets that people use to address this, which we're not actually going to talk about today, but is a very interesting topic in and of itself, is the NoSQL database. Now typically NoSQL databases allow you to scale up to larger volumes of data and also have a lot more flexibility in terms of the structure of the data that you can use with them. And then if you move up and to the right again, you start to get into Hadoop technologies. Now Hadoop is fantastic because it really allows you to deal with any type of structure with your data. So you don't have to have a pre-described schema when you're using that data. You can basically just push anything to it, and that's one of the reasons why it's so popular. And you can see also it's designed to deal with very large data sets. Now one of the other tool sets in the big data kit bag that a lot of organizations are getting a lot of value out of is the MPP database. Now MPP stands for Massively Parallel Processing, and these databases have been around for a while, but there was a real explosion of their use in kind of the mid-2000s, and now they've become a very important part of the big data landscape. And as you can see, they are designed to deal with very large data sets, but they deal with very structured data sets. So the MPP databases, at the end of the day, they are still a database, so they do need that structured data set. So the agenda for today is we're going to look at three different types of data. We're going to look at how you deal with structured data, so we'll look a little bit at the MPP databases and then specifically at the Amazon Redshift service, which is in itself an MPP database. Then we're going to move on and have a look at unstructured data, touch on Hadoop, and also look at Amazon Elastic MapReduce, or EMR. And then we're going to finish off, look at streaming data, real-time analysis of that data, and also how we address that with the Amazon Kinesis service. So let's jump into structured data, and let's have a little look at the MPP databases. Now, each of the MPP databases differ slightly in their architecture, but they all have fundamentally the same principles, which is that to get the performance that you need as your data sets grow, you really need to have an engine or an architecture that will scale out and that will allow you to get returns in terms of performance as you add more nodes to it. And so if you look at the architecture here, you can see that you've usually got some kind of leader node at the front of the cluster that really just controls the whole show. But then at that bottom layer, you've got these compute nodes that do all of the work in terms of queries. And so that's the layer that you scale out as you're looking for larger and larger data sets. And we'll look in a bit more detail later on about how that actually works. But some of the facets of MPP databases that people like is that it's ANSI standard SQL that you're using with these databases. And that's really important because most organizations have got a lot of skills in SQL, a lot of skills in business intelligence tools. And so by adopting an MPP database, immediately they can make use of the skills that they already have in their organizations. The databases are optimized for fast analysis, so as opposed to more traditional databases which are fantastic for online transaction processing type of workloads, the MPP databases really excel for analytical types of workloads where you're potentially doing lots of scans of large data sets and asking questions of your data as opposed to transacting with it. And then the third thing, which we've already touched on, is that these databases are very scalable. So you do get linear or near linear returns for on performance as you add more nodes to the system. So that's the general MPP architecture. Let's talk in a bit more detail about Amazon Redshift specifically. And first of all, let's ask, what is it? What is Amazon Redshift? Well, first and foremost, it is one of the MPP SQL databases, so it's a massively parallel engine that's ANSI standard SQL. It is optimized for analytics, so not great for transaction processing, but fantastic for analytics. And one of the lovely things about it is that you can scale it from quite small clusters in the gigabyte range, tens of gigabytes, through to multi-petabytes if you need to. And customers love this because they can start small, they don't have to invest heavily at the beginning, but they know that they've got that runway to be able to just grow the cluster as they need to. The other really important facet of the MPP databases and Redshift as well is that it's fully relational. So even though it's massively parallel, and we'll talk about some of the other things under the hood to do with the fact that it's a columnar database, etc., but at the end of the day, it's still a fully relational database. So all of the data modeling techniques that you're used to using with your traditional databases still apply here. So whatever data model works for your business, you apply that to your MPP database. The other thing about Amazon Redshift is that it's fully managed. And so what we mean by that is that Amazon will manage the infrastructure underneath the database for you. You simply tell us how many nodes you want, how big you want the cluster to be, and then we will manage deploying and provisioning the infrastructure underneath that. We'll install all the software, and then basically we will then give you access to a fully functioning, ready-to-use data warehouse of the size that you've specified. So let's have a little look at under the covers and see how it actually works. So back to the similar diagram that we had before, where you can see the basic architecture, and you've got your client tool sitting at the front there. So again, because it's a standards-based architecture, it supports JDBC and ODBC entry points from SQL tools, and that obviously means you can plug in pretty much anything into the front end there. And as I said before, the basic principle of an MPP database is that you spread the data as widely as you can across the nodes that you have. So if we look at a very simple table here, so say we've got a table with an ID column and a name column, the principle of the MPP database is that when you load that in, you spread that across all the nodes. And so you'd end up with something that looks a bit like this. And if you've done it correctly, you should see that each node has got roughly the same amount of data across the cluster. So the idea there is that then when you ask a question of the database, when you push your SQL into the system, the SQL goes into the leader node. The leader node will then do the optimization on that, create a plan, etc., and then push that same SQL out to every single node. So every node is doing exactly the same work, but it's doing it just on its slice of the data. And if it needs to share data with other nodes for joins, etc., then the nodes can talk to each other and share data so that they can resolve the joins. But the idea with every operation is that you do that at that parallel layer to make the most of all the parallel nodes that you have in the system. So once the nodes have got their intermediate result sets, they'll sit back into the node, and then they will then get passed back to the leader node, which will then merge them, sort them, and then pass that back to the client tool. So that's the basic principle of MPP, that massively parallel processing approach. Basically almost a brute force approach where you just use the parallel engine to just run as many processes as you can on your data set to resolve the query. Let's look at a couple of other attributes that Redshift has that are all designed to try and speed up your queries. And the way that it does this is to try and reduce the amount of I/O, the amount of input-output that you're doing to the disk. So typically the disk is the biggest bottleneck in any kind of analytical system, and so the more we can do to reduce the I/O during your queries, the better your performance should be. So the first thing we do is we store the data in columns rather than rows, and this is a reasonably common approach with a lot of the MPP databases, because again it's fantastic for analytical types of workloads. So if you look at that basic table that we have on the right hand side there, with a row-based database, they will store the data on the disk as your brain imagines that it would store it. So basically it writes out a row, then writes the next row, then writes the next row, etc. And that works really well for the types of access to data that transactional systems need, where they might be writing a row at a time, or looking for a single row, or updating a single row, etc. What it's not so good for is when you want to actually ask some analytical type questions. So for example, if your question is, I want to know the average amount by state, then in a row-based system you have to read all this redundant data, because you have to read the ID column, you have to read the age column before you can get to the state and the amount information for each row. So you end up reading a lot of stuff that you actually don't need to resolve the query. What happens with a columnar database is that we actually store the data in columns. So we'll write out the entire column together on the disk, and then the next column, and then the next column. What that means then is, with our query where we want the average amount by state, we can ignore the columns that we don't need for that query, and we can just go straight to the columns that we do need. So in this case we need the state, and obviously we need the amount as well. So we can read those columns, and we might read quite a few rows in there, but we're only hitting the columns that we need. So column storage is not something that you need to design for. You don't need to design it in your queries or even in your data model, but it's just interesting to know that that's the way that we store the data, so you can understand why the queries come back quite quickly. The second thing we do under the covers is we'll compress the data when we load it into the database as well. And the reason for this is that if we can get more of your data into every disk block, so a disk block for Redshift is a 1 meg block of disk, the more of your data we can fit into that 1 meg block of disk, the more of your data we can read with every disk read. And so what we'll do is we'll automatically look at your data as you load it in for the very first time. We'll look at the data type of the columns, we'll look at the makeup of the data, the way that it's sorted, etc. And then we'll choose from one of several different algorithms that we've got that we think will give you the best level of compression for the data that you've got. We'll then use that algorithm every time you add more data, and obviously we'll compress that automatically. You can override the automatic one if you wish, but usually we find that the automatic one does a great job, so you can just kind of set it and leave it. And as I said, that then obviously will save you disk space, but the real reason we do it, or the main driver for that, is really about performance. Again, not something you need to design for or worry about in terms of querying, but good to know that that's what's happening in the background. The other thing that we do to reduce I/O is we use what we call a zone map. And a zone map tracks the minimum and maximum values for each block of disk. Now, the zone map is created automatically by the system. You don't need to update it yourself or initiate the creation of it. We'll just create it for every single column in every table. And the way that we use that is that if you look at the data on the right-hand side, so imagine that that's your actual data in the table. So assuming that's some kind of ID column, and the values are 10, 13, 14, etc. And then the zone map's there on the left. So the zone map will say, okay, the minimum value you have in this block is 10, the maximum value is 324. So when we ask a query, and in our where clause we say, give us the rows where the ID equals, say, 100, then immediately we know which blocks are going to contain actual data that's going to meet the query and which blocks we can skip. Because if the value we're after doesn't fall between the minimum and maximum for that block, then there's no point in reading it. So again, simply designed to reduce the number of blocks we're reading, reduce the I/O, and try and bring back your data as quickly as possible. Now, zone maps are something that, as I said, they're automatically created, but you can make them more efficient through the use of sort keys. So we don't have time to go into sort keys here, but if you do want to get into the best practices for designing Redshift tables, have a look. You'll find some great documentation online, and we've got some great webinars that have been recorded as well, where we talk about the best way to use sort keys to really get the maximum use of your zone maps. So what's good about Redshift? What are the things that you would look to it for to really show its benefits? So basically, there's four main things that customers talk about. They talk about the performance of it. They like the scalability aspect of it, the ease of use, and then also the cost. So let's have a look at the performance. Now, this was a benchmark done by one of our customers who had a traditional SQL database that they were using, and they wanted to test out that, plus they wanted to test it out on Hive. So Hive, if you're not familiar with it, is a SQL layer that sits on top of Hadoop. So basically converts SQL-like queries into Hadoop MapReduce jobs. And then they ran the same queries on Redshift as well. So they loaded up 2 billion rows into each of those systems, and they ran a very simple query which was to essentially aggregate by month those 2 billion rows. So just show me by month the values that I want to see there. That took about 2 hours on their traditional system, about 35 minutes on Hive, and it took 12 seconds in Redshift. Now, this isn't meant to be a go at traditional SQL databases. Obviously, they're a key part of the IT landscape. It's more a statement about the fact that these types of queries, aggregating queries and summarization queries on large data sets, they're just simply not the types of queries for which those traditional databases were really designed. Whereas the MPP databases like Redshift were designed for that kind of thing from the ground up, and that's why you see that big discrepancy in performance. In terms of scalability, as I mentioned before, you can start off very small with Redshift. So the smallest node that we have is 160 gigabytes of solid-state disk, and you can create a cluster with simply a single node just when you're starting to test and play around with it. And then you can grow the cluster and you can add nodes to it if you wish, and you can also change the type of node to one that's got a larger disk if you wish to, and that will allow you then to scale up to potentially the 2 petabyte mark. So if you're not familiar with a petabyte is 1,000 terabytes and a terabyte is 1,000 gigabytes. So 2 petabytes is a lot of data, and it's nice to know you've got that runway and that headroom if you think your data set's going to grow that large. Now, in terms of ease of use, I thought I'd just quickly show you what it's like to create a cluster within Redshift. So in a second you'll see the Redshift console. So you can see I've got a cluster that's already been created, but we're going to create a new one. So this is the Redshift part of the Amazon management console. So we've just got a couple of fields to fill in. So a cluster identifier, so we can call this, we'll call this webinar. It wants to create an initial database as well, so we'll just call that demo. We'll give it the port number that we want it to listen on, set up the master user for the database, give it a password, and then on the next page, when you get there, you'll see that we've got a couple of options in terms of the node type. So you'll see the DW1s there. The DW1s are the 2 terabyte magnetic disks that we have, and then the DW2s are the smaller SSD disks, and they both come in kind of a single and an 8-pack as well. So we're going to choose the DW2 large, which gives us 160 gig per node. And then down here we're going to go for a multi-node cluster. Let's say we have two compute nodes. And the thing about the nodes is that when you specify the number of nodes, you're only telling us how many compute nodes you want. We'll always throw in a leader node as part of the cluster. You don't have to provision that or pay for it. You simply tell us how many compute nodes you want. On this page we can specify whether we want to encrypt the data in the database or not, and if we do, where we want to hold the keys for that. We can specify whether the cluster is in a virtual private cloud. We can set up alarms in here as well, and then we can go to the next page, which will basically give us a summary of what we've chosen. And then down the bottom it'll tell us how much it's going to cost us. So I'm running this in US East, and so in US East the price for that particular node is 25 cents an hour on demand. Obviously lower pricing is available for reserved instances. And so this cluster, which has got about 320 gigabytes of raw disk space, is going to cost me about 50 cents an hour. But because of compression, I'll probably get at least 2 or 3 times that in terms of my own data going into the database. So we can launch that. If we go back to here, you'll see that that database is now creating, and typically it takes between about 5 and 7 minutes to have that database up and running and ready for you to log in and start loading data. So let's talk quickly about how you integrate with Redshift. How do you get data in and out of it? So at the front end, in terms of querying it, as I said, it's ANSI standard SQL, so you can plug in a SQL editor and start writing raw SQL against the tables if you wish. Or you can plug in some kind of business intelligence tool, so Tableau, for example, MicroStrategy, Jaspersoft, Yellowfin, Cognos, Business Objects, those types of tools. Because it's standard JDBC, ODBC, they'll plug in with no dramas. In terms of getting data into it, there's a couple of options there. You can load data in from other Amazon services, so from Amazon S3, which is our storage service, from DynamoDB, which is our NoSQL service. You can load data in from Elastic MapReduce, which we'll talk about in a sec, or you can just load it in from any Linux box that can be running on AWS, or it could be running elsewhere as well. Now that's all fine for moving bulk data in, but often customers want to move data in a more incremental fashion, where they might have source systems on-premise where they want to move all the changes as they happen into Redshift. And so for that scenario, we would usually introduce some kind of ETL server. So ETL stands for extract, transform, and load. So extract from the source system, maybe transform it, and then load it into Redshift. And there's a number of partners that we have in this space that provide that ETL software to allow you to do that, and that's often called change data capture, where they're actually looking for changes on the source system to propagate through to Redshift. So how are customers using Redshift? Well, interestingly, we do have some customers who use it in quite a traditional data warehousing type fashion. So they've moved their enterprise data warehouse or the corporate data warehouse onto Redshift. But we also see a lot of very innovative uses of it, because at the end of the day, you've got this powerful parallel engine that you can run. So we see customers doing things like, for example, Channel 4 in the UK. They use it to gain customer insight into what their customers are doing with the media that they provide. So what they're looking at on the web, what they're looking at on TV, etc., so that they can better respond to customer demand. Nasdaq in the US, they use it for all their market trades. So they load up all the day's trading into Redshift, and then they do all sorts of different market analysis on that, ranging from fraud and surveillance through to analysis of the day's trading. And then MI9, which is a media company in Australia, use it for data analytics across their clickstream data, so looking at the different web properties that they have. So that was a look at how you deal with structured data. Now that's all fantastic, but if you've got some data that is a little less structured than that, so maybe it's log files that don't really conform to a particular schema, or it might be something completely unstructured like media files or video, etc., then you're not going to be able to push that straight into a database, obviously. So you're going to need some kind of service that's going to support unstructured data. And so for that, a lot of companies are looking to Hadoop for that. So let's have a little look at Hadoop and then EMR. So basically, Hadoop is a framework for processing large amounts of data. And that framework is really all about spreading the processing and the load across the available machines in the cluster. So a cluster is made up of a number of nodes, and they will then obviously take parts of the data and then work on those. So typically what you feed into your Hadoop cluster is some kind of input file, and then the actual functions that you want to run across that file. So the file gets split up and pushed into the cluster along with your functions, and then when that job is finished, it will then publish the output for you. Now, a couple of the interesting facets about Hadoop that have led to it being so popular. The first is that it's extremely flexible. So if you look at the functions that you feed into Hadoop cluster, you're dealing with very rich languages like Java and Python and Ruby, etc. And so it gives you much more scope to do really interesting things with the data, far beyond what you could do with SQL, for example. The other reason that people love it is because it's very scalable. So because the very essence of the framework is all about being parallel, then that means that as you add more nodes, the framework will very easily take advantage of those and spread that load across the new nodes that you've got in the system. The clusters are often transient as well, and this is quite interesting because we often think about databases in particular as being up and running 24/7. With Hadoop clusters, it can be a bit different. So sometimes customers will just use them in a very temporary fashion. So they'll spin them up, they'll push their data through them, they'll run the jobs they want to run, get the output, and then they'll shut the cluster down. And that's quite a common model. Some customers do run Hadoop clusters permanently, but but often people don't. They just use them in a very temporary fashion. So let's have a little look at Amazon Elastic MapReduce. Firstly, what is it? Well, basically, it's just a managed Hadoop service. And what we mean by that is that if we go back to our diagram from before, if this was an EMR cluster here, you see that the way that you interact with it is exactly the same. So you have input files and your functions and you push them in. But what's changed is that we, Amazon, are managing that cluster for you. So instead of you having to provision infrastructure, install Hadoop on every node, make sure all the nodes are talking to each other, and then finally start to actually use it, what you do instead with EMR is you tell us how many nodes you want in the cluster, what size of machine they should be, what else you want installed on it, and we will then provision the infrastructure, spin it up, make sure everything's talking to each other, make sure it's all working, and then basically present you with that running, humming cluster ready for you to use. So how does it work? So one of the things that you'll notice if you start looking at EMR is it's very tightly integrated into S3, which is the Amazon storage service. And what this means is that you can use S3 to hold the input for the cluster and also the output as well. And this has got a couple of advantages in that it protects you from any failures in the cluster. So if you've got the cluster and the data is fully contained in the cluster, and the cluster falls over for any reason, then you've potentially lost your data. Whereas if you've got it in S3, S3's got that durability, that 11 nines of durability, so you know your data is always safe. So what you typically do is you would put your data into S3. You would then choose the Hadoop distribution that you want to run for the cluster, the number of nodes, the type of nodes, and then any additional apps that you wanted running on top of that. And that might be some of the more common ones like Hive, Pig, HBase, or it might be any of the other tools that you can put on there as well. So once you've done that, and we'll run through an example in a second, you can then launch the cluster. And as with all the Amazon services, there's a number of ways you can do that. So you can do that through the console, or you can use the command line interface if you wish, or there's obviously SDKs or APIs that you can use as well. Once the cluster comes up, you can then start to use it. It can suck the data in from S3, do the processing, and then we'll also push the output back down into S3 as well. A couple of other things to note about the way that EMR works is that you can very easily resize the cluster. So even when the cluster is already running, if you suddenly decided, hey, we need a bit more grunt here, we need to churn through this data set a bit faster, you can just add more nodes to the cluster and get through your processing more quickly. The other interesting thing about keeping your data in S3 and then having separate clusters is that you can then potentially have different clusters using the same data set. And we see this quite a lot with customers who want to potentially test out different versions of their algorithm or their application on the same data set. And so they can do that very easily if they've got their data sitting in S3, because they can just spin up a different cluster and then pull a copy into S3, and that's reasonably common. The other thing you can do with S3, that you can do with EMR, which is really interesting, is use the spot market to try and drive the price of the cluster down and potentially speed things up as well. Now we'll look at the spot market in a bit more detail in a sec, but essentially the spot market is unused EC2 capacity that we have that we then allow customers to bid on. And whoever's the highest bidder can then have that particular instance for that price. And it's a great way to really drive down the price of your cluster, and we'll have a look at that in a sec. The other great thing, as I said, because a lot of customers treat their Hadoop clusters in a very transient manner, it's fantastic if you can stop paying for it once you've finished your job. Now obviously in the cloud with EMR you can do that. So once the cluster's stopped doing its business, you can terminate it and you immediately stop paying for it. Now we've talked a lot about S3 and using that as the data source for EMR. You can also keep all the data within the cluster as well on HDFS, which is the Hadoop file system, if you wish. And we do have a lot of customers that do that. So sometimes their application is such that they want to keep the cluster running all the time and they want to have the data local in HDFS, and you can certainly, EMR will support that model quite happily as well. So what's good about EMR? So some of these things we've talked about. Scalability obviously is a key one, that ability to choose a cluster as big as you want, the cost factor, and then again the ease of use, which we'll have a look up in a sec. The scalability thing we've kind of talked about. Let's have a bit of a look at cost. And I wanted to just drill down into the spot market a little bit and show you an example. So if you look at the scenario here where you have a 4-node cluster, and that takes about 14 hours to do the particular job that you've given it. And so if you look at the cost for that, you've got 4 instances and you're running them for 14 hours and they cost 50 cents each, and that's going to cost you $28 to run that process. Now in scenario 2, you keep your initial 4 instances, but you also add to that 5 more spot instances. Now what then happens to the duration of your job is that it comes down to, let's say, 7 hours, because obviously when you introduce the spot instances, you've introduced more compute power to the cluster, and that allows you to obviously get through things much more quickly. The other interesting thing that happens though, if you look at the cost, is we're now running our initial 4 instances only for 7 hours rather than for 14 hours. So those 4 instances at 7 hours and at 50 cents comes out to $14, and then you add in the cost of the spot instances. So let's assume, for the sake of this example, that we got them at half price, so we bid 25 cents for them, and we were successful. So those 5 instances for 7 hours at 25 cents is $8.75. The total brings it to $22.75, which is obviously less than our original scenario 1 cost. And so the upshot of that is that we got time savings of 50%, so we got through the job in half the time, but it also cost us less to run as well. So now you're thinking, well, that sounds too good to be true. If I can save money and time, then why doesn't everyone do that? Why don't I just do that all the time? Well, the catch with the spot instances is that if you are outbid for that instance, then we will take it away from you. So what that means is that you need to be able to use them in a way where if they do get taken away, it's not going to interrupt your processing. So the way that we do that in EMR is, if we just look inside the EMR box for a second, you'll see there's several different instances within an EMR cluster. So at the top here, you've got your master instance, and that controls the whole cluster. And then on the left, you've got the core instances. Now the core instances have HDFS attached to them as well. So if you're using the cluster permanently and storing the data in HDFS, your data will live there. Or if you're using S3 as your main source for the data, we'll use the HDFS in here just for temporary files as we go about the processing. But you'll see the third instance on the right there are the task nodes. Now the task nodes, you'll see, have got no disk attached to them. They're pure processing engines, and so what they're designed to do is to allow you to speed up the processing in the cluster, but in such a way that if you lose one, then it's not going to bring the cluster down. Because what will happen is, if the master instance has assigned a task to one of the task instances, and that task instance goes away, then that job will obviously not be completed, and then the master instance will simply give it to another instance. So your cluster keeps running and the job just takes slightly longer. So the upshot of all of that is those task instances are great for using for the spot market. So we have some customers who spin up very large clusters, enormous clusters, and most of them are running on spot, and they're able to crunch through their processing very quickly at quite a low cost. Just wanted to quickly mention the Hadoop ecosystem. So if you follow the Hadoop space at all, you'll know that every 10 minutes there's a new library or open source project or third-party plugin that sits on top of Hadoop. The ecosystem is very rich and very broad, covering everything from SQL layers to machine learning algorithms, log collection agents, etc., you name it. And the great news there is that because Amazon uses the pure Apache Hadoop distribution, you can plug in pretty much whatever you like. And in fact, we try and make that as easy as possible for you by providing a lot of these essentially out of the box when you actually start the cluster. So let me just quickly show you starting up a cluster with EMR. So let's go over to the console, and then hopefully your screens will catch up soon. Okay, you should be able to see that now. So basically, I'll just run through this. Now, there's a few options here, so I'm not going to go through absolutely everything, but there's a few key ones I want to point out to you. So basically, we're going to create a cluster. We're going to give it a name. We won't worry about logging. You can put tags on them. And if we come down here to software configuration, you can see that we can choose the Hadoop distribution. You can go with the Amazon one, or you can also go with the MapR distribution as well. And then underneath that, if you look at applications to be installed, you'll see that by default we'll install Hive, Pig, and Hue for you. So probably the most used applications with Hadoop. But there's also some additional ones here in this drop-down. So if you want to install HBase, Impala, Ganglia, or Hunk, you can simply just select that and we will install that for you. So by the time your cluster comes up, those applications will be in place. And then if we come down to hardware configuration, you can put this into a virtual private cloud if you wish. And then if you look at the different instance types, you've got your master, your core, and your task instances that we talked about. And here I've just opened up the box to choose the instance for each of those. And so you can choose these independently, but you can see that you can choose from a very large range of different instance types depending on whether you want more memory, more CPU, more disk, etc. And here's where you can say how many you want, and then just wait for you guys to catch up, see how many you want here, and then also potentially put in a request for spot pricing as well. So if you say you want request on spot, tell us what your bid price is, and then we'll go from there. The other thing I'll point out is if there's a particular add-on to Hadoop that we don't have in the drop-down that I showed you, you can still add that through a bootstrap action. So basically you just provide us with a script that tells us where to grab the files from, and then we'll install that for you as well. Okay, and then we can kick that off and install that cluster. So going back to the presentation, so how are customers using EMR? Well, basically, if you look at not just EMR but Hadoop generally, it's become so popular because of some of the facets we talked about in terms of flexibility and scalability that almost every vertical's got some kind of use case that they're using with Hadoop. And you can see some of the examples there. A couple of our own customers using EMR. Yelp's a good example. So that is a site in the US where you can recommend hotels or restaurants, etc., and they use EMR extensively to look at the logs to do the recommendation engine. FourSquare use it to have a look at the data coming out of their mobile app to see where people are checking in, etc. And then we've got people like Getty Images, for example, using it to rank photos so that when customers are searching for a particular image, they can bring up the most relevant images based on the ranking that they've used with EMR. So that's just scratching the surface in terms of use cases. There's lots of fantastic use cases and case studies and stories around the use of EMR and Hadoop. So let's just quickly talk about streaming. So we found within Amazon that we were starting to talk a lot about streaming and real-time data as opposed to batch processing, and that obviously was important to us internally because you can imagine we generate a lot of data as customers use infrastructure. And then so we went to our customers and we asked them what they would do with a real-time engine. And we spoke to people in different industries, but we found that the patterns that they were talking about were similar. So the first thing that people talked about at the most basic level was simply just ingesting logs. So they said, look, you know, we generate a lot of logs from servers or clickstream. We just want somewhere where we can actually stream the logs in that will hold them durably and then write them to a log for us, like durably to an audit log. The second one, though, was continual metrics. So people wanted to potentially look into the stream and pull out some of the data to then look at some KPIs, whether that was looking at operational metrics as they were happening, what's happening in the last 10 seconds with machines, temperatures, etc., etc. Then there was more, some customers wanted to get into deeper analysis, some more kind of analysis to do with things like fraud monitoring, user engagement, that kind of thing. It was a little bit deeper. And the fourth one was where people really went to town and got into complex event processing, etc. So we saw that there was a big need for an engine that would basically allow people to capture data and then do some of this analysis. So we went away and then released a service called Amazon Kinesis. What is Kinesis? Well, firstly the name, let me explain that. So the name really refers to the fact that a kinesis is a movement or activity in response to a stimulus. And so when you look at what the service does, again, it's a fully managed service, and it's really for allowing you to do real-time processing of very high volume data that's streaming towards you. How does it work? Well, basically, what it allows you to do is take the different data sources that you might have that will be producing data and push them into the Kinesis service. So the first thing you'll notice about Kinesis is it sits across 3 availability zones. Now for us, an availability zone you can think of as a separate physical data center, so separate floodplains and electricity grids and all that fun stuff, which means that each of your messages is written 3 times before we'll acknowledge it. You create a stream within the Kinesis service, and that then gives you an endpoint where these data sources can then push their data. What we'll then do is we'll then hold those messages in the stream for you for 24 hours, then allowing you to write applications and consume that data at the back end. So one of the typical patterns we see is some people, for example, writing that logging application that we talked about, and all it's doing is just reading from the stream and writing out an audit log to S3, or maybe that metrics app. So these apps are running on EC2, so that might push messages into Dynamo, for example, for a real-time dashboard. You then got your analysis app that's pushing data into Redshift for deeper analysis, or then potentially some kind of machine learning application that's pushing into something like EMR. So we've produced connectors for obviously a lot of Amazon services, but there are other third-party services that we support as well. And so the idea is that each of these applications works independently of one another. They're not interfering with one another. So when one of them reads a message from the stream, that message stays in the stream for other applications to read until after 24 hours it expires. So just quickly putting data into Kinesis. Once you create the stream, you've then got the concept of a shard. So a shard gives you your unit of scaling. So each shard will give you 1,000 transactions a second, or 1 megabyte a second. You've got a 50K payload, and as I said, the messages are kept for 24 hours. You also give us a partition key, and that determines which shard that particular message will go to, and that helps at the other end for the consuming application, so you can group messages together. And we'll also give you a unique sequence number. So we'll also guarantee order with Kinesis as well. So whatever order you put your messages in, that's the order that they'll come out the other end. In terms of getting data out, we've provided a client library to try and help make that process easier for you, so that you can focus on writing some interesting apps as opposed to getting knee-deep into the API. And that's currently available in Java and Python, although obviously you can write to the lower level SDKs in other languages if you wish to as well. What's good about it? So essentially, again, as a managed service, you've got that easy administration. So with a couple of clicks, you can create a stream with some shards in it, and it's ready to go. It's real-time performance as opposed to batch. So it means that you can capture those messages and then act on them in near real time. Very high throughput, so you can scale it up to as many messages a second as you need to. And then the integration I talked about, so we've released connectors for some of our own services such as S3 and Redshift, but also there's connectors for Apache Storm, Elasticsearch, and others. It allows you to build those real-time applications. So we've tried to abstract you from some of the complexities of the API, so that you can just focus on building those real-time apps, and then low cost as well. So if you look at the cost of the service, it's quite low compared to obviously trying to manage that infrastructure yourself. How are customers using it? Lots and lots of different applications for Kinesis. A great example is a company called Supercell, one of the big gaming companies. They use it for gaming analytics. So whenever a user hits a milestone in a game or an event is fired, they want to capture that and do something with it. Snowplow is a partner of ours out of the UK. They've produced a framework that sits on top of Kinesis that allows you to capture events from Clickstream, for example, or from mobile, and then act on that in real time. And then the Black Dog Institute down here in Australia has used Kinesis for sentiment analysis, so looking at tweets that people have sent and trying to group those in terms of sentiment based on location. So we're coming up to the hour, so I just wanted to finish off. I wanted to put this URL out for you guys. So if you go to the Big Data landing page at Amazon.com or AWS Amazon.com, you'll see links to the documentation, more detail on each of the services, case studies, videos, etc., a wealth of information. So please find all that stuff there. If there's stuff there, or if there's stuff that's not there that you would like to be there, please let us know. And then in terms of extra training, so there are online labs that you can do. Some of those are free. There's also instructor-led classes as well. If you go to the training landing page, it'll talk about those. There's a big data specific class now as well that's instructor-led, and obviously there's the certifications as well. So there's the training URL down the bottom there. And finally, we would just like to thank you very much for attending this particular session, but also any other sessions that you've attended this week. We do appreciate that everyone's very busy, and so we're very appreciative that you've spent this hour with us. We've hoped that you found that useful, and obviously we appreciate your feedback. So thanks again, and hopefully we'll see you soon.